It had not looked back in 13 years, not once. Not toward the small blue world it launched from, not toward the sun that had powered every instrument it carried since the day it left Cape Canaveral. For 13 years it only looked forward, past Jupiter, past Saturn, past the orbit of everything humans had ever touched. Then, on a Wednesday in February, a team on the third floor of a lab in Pasadena sent it a single command: turn around, not to search, not to explore, just to look, one last time, at the place it came from. What came back 34 minutes later would become one of the most reproduced photographs in human history. But it would also start a chain of discoveries that 3 decades later, scientists still cannot fully explain. A signal from beyond the edge of the solar system that shouldn't be there, coming from a machine that was never built to find it. This is the real story of Voyager 1. On February 14, 1990, at 0448 Greenwich Mean Time, engineers at NASA's Jet Propulsion Laboratory in Pasadena, California, executed a command sequence 11 years in the making. Voyager 1, already 3.7 billion miles from the Sun, pivoted its narrow-angle camera back toward the inner solar system and began photographing the planets it had left behind. It was not part of the original mission. It had been fought over for a decade, and it was almost never approved. The distances involved are difficult to hold in the mind. 3.7 billion miles. 40 times the distance between Earth and the Sun. At that range, Earth would not appear as a planet. It would not even appear as a shape. It would appear as less than a single pixel, a fraction of 0.12 of a pixel, according to NASA's own imaging data, a smudge of light caught inside a scattered sunbeam by accident. Nobody expected the picture to matter scientifically. That was the entire objection. Consider what 34 minutes of camera time actually captured. Neptune, Uranus, Saturn, Jupiter, Venus, Earth, 6 planets and the Sun itself, photographed in a single sequence from a vantage point outside the plane every one of them orbits in on, a perspective no probe before or since has occupied while looking back at the whole system at once. Mercury was lost in the Sun's glare. Mars barely registered, its light scattered into nothing by stray sunlight bouncing inside the camera housing. Of everything the solar system contains, this was the only portrait of it ever taken from the outside looking in. Voyager 1 launched on September 5, 1977, from Cape Canaveral, one of 2 nearly identical spacecraft sent out to use a rare planetary alignment that occurs roughly once every 175 years. Its twin, Voyager 2, took the slower route. Voyager 1 took the faster one, reaching Jupiter in March 1979 and Saturn in November 1980, sending back the first close images of Jupiter's storms and the fine structure inside Saturn's rings. By the time it passed Saturn's moon Titan, its primary mission was, by NASA's own definition, complete. That was when Carl Sagan, a member of the imaging team, made his case. He had proposed it as early as 1980, EIOTS, turn the camera around before it's powered down forever and take one photograph of home. Not for data, for perspective. Many engineers pushed back. Pointing a delicate optical system back toward the Sun risked burning out the camera entirely. There was no scientific return in a picture of a pixel. For nearly a decade, the idea sat unapproved. Unknown to Sagan at the time, planetary scientist Carolyn Porco had independently begun raising the same question inside the Voyager program after joining the imaging team in 1983, asking as early as 1985 whether such a photograph was even technically possible. 2 scientists working the same problem from different directions, arriving at the same conclusion, that the picture was worth the risk, even without a research justification behind it. 9 years passed between the first proposal and the final command. Then, in 1989, with Voyager 1 approaching the point where its imaging system would be shut down permanently to conserve power for the instruments that mattered for interstellar science, the request was finally granted. The sequence was built by imaging scientists Candace Hansen and Carolyn Porco. 60 frames, 6 planets, 1 star. All from a vantage point no human instrument had ever occupied, outside the plane of the solar system, looking back in. The images were taken at 4:48 Greenwich Mean Time on February 14, 1990. Voyager 1 powered its cameras off for the final time 34 minutes later at 5:22 Greenwich Mean Time. It would never take another photograph again. It took until May 1st, 1990 for all 60 frames to arrive back on Earth, 4 separate transmission passes through NASA's Deep Space Network, each signal crawling across the solar system at the speed of light, delayed further because 2 other missions, Magellan and Galileo, had priority use of the antennas. When the frame containing Earth finally resolved, it showed almost nothing. A blue-white speck smaller than a period on a printed page, suspended inside a band of scattered light. An optical artifact caused by the camera pointing too close to the sun to properly shield itself. Sagan later wrote about that speck in a passage that outlived the mission itself, that everyone who had ever lived, every war fought, and every empire built had happened on that single point of light, a mote of dust suspended in a sunbeam. The photograph had no scientific value. Everyone involved in approving it admitted as much. But something else was already happening to Voyager 1, something with no poetry attached to it at all. By December 2004, Voyager 1 had already crossed the termination shock, the point where the outward-blowing solar wind abruptly slows as it collides with the thin gas of interstellar space. That was still solar system territory. The true boundary lay years further out. 22 years after the pale blue dot photograph in August 2012, Voyager 1 crossed a boundary no spacecraft had ever crossed. It was the heliopause, the outer edge of the sun's magnetic influence, the true border where the solar wind gives way entirely to the pressure of interstellar space. Confirmation didn't come immediately. It came in September 2013, when a solar eruption from months earlier finally reached the spacecraft and triggered oscillations in the surrounding plasma. Physicist Donald Gurnett of the University of Iowa, principal investigator on Voyager's plasma wave instrument, used that oscillation to calculate the density of the material around the spacecraft, and confirmed what the data had been suggesting for a year. Voyager 1 was no longer inside the solar system. It was in the space between stars. The density readings alone were startling. Interstellar plasma turned out to be roughly 40 times denser than the solar wind Voyager had been traveling through for decades. A sharp, unmistakable transition, exactly where theory said it should be, and yet still strange to confirm directly for the first time in human history. It is, to this day, the most distant human-made object ever built. And that is where the story stops being about a photograph and starts being about something researchers still cannot fully account for. Voyager 1's plasma wave instrument could only detect the density of interstellar space when something violent happened. A solar shockwave, a coronal mass ejection, some outburst from 90-plus astronomical units away finally reaching the spacecraft and rattling the plasma around it. Between those events, there was nothing to measure. Silence. Then, in 2017, the silence stopped being silent. Cornell doctoral student Stella Koch-Acker, examining years of data from Voyager 1's plasma wave system, found something that shouldn't have been there in the gaps between solar events. A signal. Faint, narrow, continuous, a hum, not triggered by anything, not caused by the sun, present, low-level, and constant. A persistent vibration in interstellar gas that Voyager 1 had apparently been recording for years without anyone noticing it was there. Acker published the findings on May 10, 2021 in the journal Nature Astronomy, alongside senior researcher James Cordes, co-author Shami Chatterjee, and colleagues Donald Gurnett, William Kurth, and Stephen Spangler from the University of Iowa. In Cordes' words, the interstellar medium had previously only been visible to Voyager during violent events, like detecting a single lightning strike inside a thunderstorm and nothing else. What Acker had found was the rain in between the lightning. A background hum of plasma that had simply never been detected before, because no one had a reason to think it existed at all. Chatterjee put it plainly in the university's own statement on the discovery. The spacecraft no longer needed a solar outburst as an excuse to report back. Regardless of what the sun was doing, 90-plus astronomical units away, Voyager was sending detail continuously, the density it was moving through, updated again and again and again. 14 billion miles from Earth. A 44-year-old spacecraft with a working power budget smaller than a household light bulb was quietly recording the ambient hum of the galaxy, in a frequency band no instrument had ever been sensitive enough or patient enough to isolate. The discovery meant something larger than a curiosity. It meant scientists no longer needed to wait for a solar outburst to measure what Voyager was moving through. They could track it continuously, density, structure, turbulence, second by second, for as long as the spacecraft kept transmitting. But it also raised a harder question. If the interstellar medium was humming steadily where no model expected activity, what else about the space just beyond our solar system had been built on incomplete assumptions? That question is where Boston University astrophysicist Merav Ofer enters the story. Ofer has spent years challenging the textbook picture of the Heliosphere, the bubble of solar wind that Voyager 1 had to cross to reach interstellar space. The traditional model, taught for decades, described it as comet-shaped. A rounded nose facing forward, a long trailing tail stretching backward, like a windsock streaming behind the sun as it moves through the galaxy. Using data pulled from both Voyager spacecraft, alongside particle measurements from NASA's Cassini and IBEX missions and newer three-dimensional modeling, Ofer has argued the shape may be entirely different. Not a tail, but something closer to a deflated croissant, folded and asymmetric, its structure shaped by magnetic pressures scientists hadn't fully accounted for. The two Voyagers, it turns out, didn't even exit through matching terrain. Voyager 1 crossed the heliopause in 2012 at one location. Voyager 2, crossing independently on November 5, 2018, found different plasma conditions at its own crossing point, a discrepancy that, on its own, hints the boundary isn't the smooth, symmetrical shell early diagrams once implied. If Ofer is right, then the boundary Voyager 1 crossed in 2012, the very edge scientists have spent a decade studying, isn't shaped the way most published diagrams still show it. The bubble protecting every planet in the solar system, deflecting the more dangerous forms of cosmic radiation, may not be the shape humanity has pictured since the concept was first proposed. It's a serious hypothesis built on Voyager's own instruments, argued at NASA-associated research institutions, not fringe. But it is not settled. Other researchers, including members of Ocker and Gurnet's own teams, urge caution. The hum itself, they stress, is not exotic physics. It's a known category of plasma oscillation, simply detected at a lower amplitude than anyone had previously tried to measure. Cordes has compared the interstellar medium to a quiet, gentle rain, interrupted occasionally by the lightning of a solar outburst. What changed in 2021 wasn't the physics. It was the sensitivity of the listening. The heliosphere shape debate is similarly bounded by real disagreement, not speculation. Some researchers back Ofer's asymmetric model, others argue the classic comet tail picture still fits the majority of the data once measurement uncertainty is accounted for. It remains an active argument inside peer-reviewed literature, unresolved, not a rejection of the standard model, and not evidence of anything beyond ordinary plasma physics operating at a scale humans have only just begun to measure directly. Voyager 1's instruments are also 49 years old, operating at the outer limit of their design life, on a power supply NASA expects to fully deplete before the end of the decade. Each remaining instrument draws power the spacecraft can no longer spare in full, and mission engineers have already begun shutting systems down permanently, one at a time, to keep the plasma wave instrument and the transmitter alive as long as possible. Every reading from this point forward is treated with the caveat that the equipment gathering it was never built to still be running. What is not in dispute is this. A spacecraft launched during the Ford administration, carrying a golden record of human sounds in case anything out there ever found it, is still transmitting usable science from farther away than any human object has ever traveled. And what it is finding does not match what anyone expected to be there. Stay with that a moment. A machine built with 1970s computing power, running on less processing capability than a modern key fob, turned its camera around once in 1990 to show us how small we are, and then, without cameras, without fanfare, kept listening long enough to hear something in the dark that nobody knew was humming. Voyager 1 is now more than 15 billion miles from Earth. Its radio signal, traveling at the speed of light, takes over 23 hours to reach the antennas built to receive it. It is still moving outward, into a region of the galaxy no instrument built by any civilization has ever sampled before. It carries almost nothing by modern standards. 8-track digital tape. 69 kilobytes of computer memory, spread across 3 onboard computers that together have less processing power than a musical greeting card. And bolted to its side, a gold-plated copper record, Sounds of Earth, greetings in 55 languages, whale song, a human heartbeat, assembled in 1977 on the chance that something, someday, might intercept it long after its instruments have gone quiet and its makers are gone. For now, it is still working. Still turning starlight and static into numbers, a handful of scientists on the third planet from the Sun spend their careers trying to decode. Every year, NASA engineers switch off another instrument to conserve what power remains, rationing a machine that has already outlived every projection made for it in 1977. Somewhere in that data, in the hum Ocker found, in the shape Ofer is still arguing over, in the terabytes still waiting to be analyzed from a machine humanity may lose contact with within the decade, there may be an answer to a much larger question, not what the edge of our solar system looks like, but what surrounds every star system like ours, waiting quietly in the dark, until something finally turns around to listen. If you want to understand what Voyager found on the other side of that boundary, and why some scientists think it changes what we thought we knew about the space between stars, that's a story for next time. For now, the hum continues. Faint, steady, 14 billion miles out and still coming in.